here's a sign. I pulled this off a Google search, so I don't know where exactly it is. It's 6% grade. 6% grade. They often put these right before there's like a 5 or 6 mile stretch of 6% grade. What does that mean? What does that mean? What does that? Don't worry about it. Come on in and join us. What does 6% grade mean? I mean, obviously it's going downhill. It's going downhill, right? Quincy, go.
The incline or the decline?
Okay, so what is this? I love it. So it's either a decline, it's an incline if you're driving the other way. It's a decline if you're going down like the truck is. And they often put what at the bottom of these 6% grades? Those big runoffs. Those big runoffs with the crazy gravel pits. So in case the trucks lose their brakes, they can go down there and not keep going and cause mass havoc. But I want to quantify this 6%. What does that mean? What exactly does that mean? Say it again, please. Say it again. Oh, I'm sorry.
6% different than being completely flat?
6% of what?
Level.
Of vertical? Or horizontal? So, what would 100% be? If it was 100, in order to, for percent with this,
Yeah.
so 6% would be like going 6% of that 100. That's actually not what it means. That makes logical sense, but that's not what is used here. It's actually a much simpler idea, believe it or not. What do you think? Farrah, you're going to say something. Go ahead.
It's based on 90%, because 90% is a right angle.
90% is a right angle. What percent is 90? What percent grade is a 90-degree angle? It's a trick question. It's a trick question. I'm going to cut this for a second. A 90-degree angle is vertical. Tell me your name again. Yes. Cheryl. I was going to say Shelby. Cheryl. I knew it was 6 letters. I just remembered that for some reason. It's based off of a right angle, but a right angle actually doesn't have a grade. So a vertical road, if a vertical road existed, which thank God it doesn't actually exist as far as a grade measure goes. So here's a road. Here's a road. Here's a road. And this is not drawn to scale at all. At all. This is horribly not to scale. And here's your 90-degree angle. The 90-degree angle, for sure, has something to do with what's going on with the grade. Let me see how is that showing up on the camera. It's not bad. I'm going to turn a little bit of light up. Okay. Now the question is, where is the 6%? Okay, 6% grade. Because we often encounter these. We often encounter these as we go through our driving over the passes coming in from the east, from the west. Okay, so where's the 6%? Where's the 6%? What does 6% mean? What does that mean? 6%. What does the percent stand for? Per 100. 6% is, as a decimal, is 0.06. As a fraction, which I like to think about a little bit more here, is 6 per 100. Now that's a ratio of 2 numbers, 6 over 100. These numbers don't necessarily have any units attached to them, but you can apply the same unit to both of them, and the ratio will be maintained. So if I call this 6 feet over 100 feet, that's the same as just 6 over 100. Because if you think of it from a mathematical point of view, the units, this is not really good logic, but the units cancel. If that kind of makes sense. You'll have a whole project devoted to this, your second project devoted to this. But I could easily make it 60 feet over 1,000 feet. Wouldn't that be the same ratio? I could make it 0.6 feet over 10 feet. You're being very English right now. Yes, metric system. 2 decimal points. Yes. You can also get away from feet. You can use meters. You can use miles. Use anything you want. Very often, these things deal with a 5-mile stretch of road. Very often, right? So you can also have. Let's see what we can do over here. You could have 6 miles over 100 miles. That's feet. That's a Spinal Tap moment right there. 6 miles over 100 miles. So anyway, the idea of grade is that you've got some kind of mile ratio, 6 to 100. Where is the 6 and where is the 100? So here's the road. Here's you and your car. Well, there's your car. There's a 1956 Bel Air. The door handle. Where's the 6 and where is the 100? Please tell me your name.
Echo.
Echo. That's right.
100 is the distance distance along the road, so 6 is the amount of distance up in elevation.
Awesome. And we give those special names in math, don't we? There it was. It's the rise and the run. It's the rise and the run. Yeah, that's what. So this guy right here is the rise, and this guy right here is the run. Now, what's clever is when you're in your car, on average, you're not driving on either the rise or the run. What are you driving on? Do you know what that funny other piece is called in a right triangle? There's the one. It's the hypotenuse. This guy's the hypotenuse. It's the hypotenuse. You're actually traveling on that, unless the road is perfectly flat. If the road is perfectly flat, you're then driving on the run, essentially. But then there's no grade to talk about. It's 0 over a run. And you can see now, if you're driving on a perfectly flat road, the grade is 0, because there's 0 rise over run. So as a more informal definition of grade, tell me, I did. We did, yeah. As soon as I talk about allergies and honey and stuff. So grade is essentially just the rise, Gesundheit, over the run, which you guys have been for years calling slope. But for some reason, when they make traffic signs, they call it grade. It's the same as slope. So now, can you see why earlier I said a 90-degree road wouldn't have a grade? A zero degree road has a 0% grade because there's no rise and plenty of run. Why would a 90-degree road, if such an animal existed, have no grade? It's an undefined grade because it's all rise and no run. Because you've got a number here and a 0 here. Well, you can't have that now, can you, in mathematics? That's undefined. It's a great word. Tell me your name again. Mike. I was going to guess. You just guessed. So if it's rise over 0, it's undefined. If it's 0 over run, it's 0. Horizontal. Now, with that in mind, let's go back to, I heard somebody say 100% earlier. What would a 100% grade look like then? What would a 100% grade look like? What would a 100% grade be? It's not this. What is it? It would be steep. Now, it's a good word. It's a good word to say steep. When you get the answer for it, you might not think it's steep until you try to ski this. Tell me your name, my friend.
Benjamin.
Say again? Benjamin, go ahead. What's 100% grade?
It'll be a 45-degree
It's a
angle.
45-degree angle is 100% grade. Here's why. Okay? This is a bit of a geometry review. You might not like this, but it'll only hurt for like 30 seconds. If you draw a road that's angled at 45 degrees, and this is 90 right here, what does that angle up there have to be? This might hurt a little bit, just remembering this. Has to be 45 as well. They have to sum up to 180 degrees, which is something you learned a million years ago. 3 angles of a triangle have to sum to 180. Now, this is a right triangle, just like that one is, because it has a right angle in it. But this one's also special because these 2 angles are the same. That makes it isosceles. And what that means is these 2 sides are the same length. These properties are used very often when they're putting roofs on houses, because the two pitches have to have the same length, if you will. Not necessarily the same, well, it depends on the type of roof you're building. But very often you'll see this kind of rotated around. This is called a 12-12 pitch. 12-12 would be 100% grade. And the reason it's called a 12-12, I'm not sure why they use the 12, maybe it's 12 because 12 inches in a foot, I'm guessing. Is that what it is, 12 inches in a foot?
Rows, yes, because there's 12 inches in a foot.
Perfect. 12-12 pitch simply means that this and this are the same, both 12 inches in this case. So your rise and your run are both the same. Well, if your rise and your run are both the same, you've got the same number here as here, which means the ratio is 1. So instead of 0.06, it would be 1, and 1 as a percent is 100%. So a 100% grade would be a 45-degree angle. So when Mike said steep, hell yeah, if anybody's ever walked on a 45-degree angled roof, it can be terrifying. That doesn't seem that steep, because you think 45 degrees. I mean, you look at your piece of paper in your notebook and fold it over and make a 45. It's like, not that bad. Have you ever skied a Black Diamond up at Bachelor? They're not quite 45. They're just under 45 degrees. In the backcountry, we studied the avalanche slides in the backcountry. The slide zone for avalanches is well under 45 degrees. So it's all a matter of perception. When you think about 45, you're like, oh, that's not that steep. Very few stairs on this campus are that deep. I'm looking at the ones they just put in over there. They're nowhere near 45 degrees. They're very long this way and very, very not so long this way. The steps in Ochiko.
Yeah.
Yes, those. Yes, those. They're not 45 though. They're closer to 45 than those are, and they're also not the code. I'm sure they're getting ripped out, you know. But so yeah, a 45-degree angle would be a 100% slope. A 200% slope. Now that's a little bit tricky. You have to use trigonometry. I'm going to guess it's about a 62 or 63-degree angle. But what would a 200% grade? What would a 200% grade look like? Describe it in terms of this triangle. If it was a 200% grade, what would this look like? If it were a 200% grade? Oh, very nice. Because if it's 200%, Echo.
Then the run is only 100, and then the rise is 2.
Perfect. The rise is 2 units where the run is 1. That's perfect. Perfectly said. So we'll look more like this. We'll look more like this. This would be 2 units, and this would just be 1 unit. And I don't know what unit it is, whether it's feet, miles, inches, whatever. Hectares. Hectares is something like that's an area. Whatever unit you're using. So, one other thing to kind of take away from grade, saying that it doesn't matter what unit you use. I drew this to whatever scale I drew it to. This is nowhere indicative of how big this angle should actually be. A 6% grade, swing the camera around here. A 6% grade should look something like this. So let's call that 100. You guys tell me where to stop. If that's 100, where's 6 going to be? Tell me where to stop. We're about there?
Yeah, maybe.
Ish? Yeah? Pretend that's a straight line. An ish. So here's 100 units. There's an I in there. Here's a right angle. Here's 6 units. There's 100% grade. That's 100% grade. So you look at that, and I mean, it's not drawn perfect. It's drawn much better to scale than that is. The actual angle formed is somewhere around 3 degrees. 3 degrees is small. Exactly. It's very, very small. So why would they put these signs in front of a road that has a grade like that? What do you think, Hannah?
Because given enough speed and distance, you can get a lot of momentum going, and if you don't have brakes, you have no way of stopping.
So that's a fantastic point. I love that. Behind you, what's your name, my friend?
Kate,
Kate, go ahead.
they probably also use the same signs no matter what the grade is.
Oh God, I hope not. God, I hope not. I hope not only because underestimating a grade. Well, I'm trying to think of examples. I know there's a 7% grade sign in Pennsylvania. There's a set of mountains in the Poconos I ride my bike over. 7% grade. There's no sign on Mackenzie Pass, is there? Is there a grade sign on Mackenzie Pass? I've done the average grade of that one, and you will too, on one of your take-home assessments. It's not 6 or 7. Now here's another deal too. Here's another deal too. Sometimes when they put those signs up, they're not giving you the grade at any given point. For example, one way to kind of misuse a 6% grade would be to measure the rise and the run from a beginning to an ending point. So in other words, if you start here at 0 rise, and you go 100 units of run, but the road does this. On average, that's a 6% grade. Because from the time you started to the time you stopped, you netted 6 feet of elevation gain. And from the time you started to the time you stopped, you netted 100 feet of run. So on average, that's a 6% elevation gain. Of course, you did a lot of gaining to get. This is why any round trip you take has a 0% grade. I don't care if you drive your car from here to Bachelor and back. If you start and stop in your driveway, that's 0% grade, isn't it? Because you came back to the same place you started. No matter how much your run is, your rise went from 0 to 0. Now, that's why a lot of tracking software will measure overall gains in elevation. So they'll measure all of this. Every time you're going up, they'll measure all that climbing, and they'll give you an absolute grade, not an average grade. So this thing has an average grade of 6 units. Because what an average actually does is, it assumes, let me get a different color marker over here. An average grade just assumes that you get from point A to point B in a linear fashion. In a linear fashion. So you're doing this on average. The easiest, most linear way of getting there is the average. Now you can kind of see why it would average out. Clearly, some of those parts are much, much steeper than 6%. But some of those parts are also negative, aren't they? Some of those grades are negative, aren't they? The ones where you're going down. Technically speaking, that sign that says 6% grade, that's just the truck going down, that's a negative 6% grade, because you're dropping. Think about slope. Slopes can be positive or negative. They're positive when they're rising left to right, and they're negative when they're falling left to right. So all those positives kind of, if you will, cancel with the negatives. And on average, you go up 6 units for every 100. Now, averages can be deadly. Averages can be deadly. You tell somebody, go ahead, it's plenty safe to cross that stream. It's got an average depth of 2 feet. Totally fine. That might mean that it's 2 inches wide, or 2 inches deep for 95% of it, and then it drops off to 8 feet when it puts current for the last whatever. But on average, it's 2 feet. Right? So averages, you have to be careful. Very often, though, the roads don't do this when you see those signs. They're very controlled grades for that entire time. But just heads up, this idea of an average is going to come back to us throughout this entire class. Because the idea of an average is something that's going to come to you guys pretty much your entire life. Yes, good? Ish? All right, good stuff, good stuff, good stuff. So, I want to come back to this diagram. We're still recording okay? Yep. Not bad, not bad. So, I want to come back to this diagram. And I want to test one more thing about grade before we get into the remainder of the talk today. Here we go. So, here's your hypotenuse. Here's the run. Here's the rise. Let's insert our numbers in. Let's insert our numbers in. Take the car away. Take the car away. Let's use the 6 and 100. And it doesn't matter if we use 6 and 100, 12 and 200, 18 and 300. It doesn't matter because they all have the same ratio. And they're all going to generate the same angle out here. And I know this angle's too big. I know it's too big visually. That's closer to that red angle over there. But we'll just use this because it's easier for the camera to see it. Is the camera seeing it? Ish. Okay. So let's call this 100 feet. And let's call this 6 feet. And let's figure out how much distance you actually travel if you travel 100 feet of run over 6 feet of rise. So you're not driving either of these things. On a road with a positive or negative grade, a non-zero grade, you're actually traveling on this part, aren't you? So what I want you guys to know is, or I want you to figure out, is what's that? What do you actually travel? And this is a result from geometry you may have forgotten. It's possible you've forgotten this. But it's important to remember this because this actually does come in handy. I recently had a geometry student send me an email that he used this in building a garden for his house back on the East Coast. So this is actually fairly useful for like everyday things. At least it can be fairly useful for everyday things. I used it to build the door of my chicken coop out of 2x3s rather than going and buying a prefab door. I had a bunch of scrap 2x3 around, and I used the result to do this, to build a door with a big cross brace and this big zigzag braces that shores it up. Use the result that we're talking about right now. What would you use to figure that out? I'm hearing whispers of a beautiful, beautiful mathematical theorem. Tell me your name, my friend. Matt, my friend, go.
A squared plus B squared equals C squared.
What is Matt talking about? Why is it called the Pythagorean theorem?
I have no idea.
Because it was discovered by the Chinese 1,000 years before Pythagoras was even around. How did Pythagoras get his name attached to it? He slept with somebody. Must have. And crazy Greeks and their vegetarian lifestyle. No, Pythagorean theorem, yes. Pythagoras gave us this beautiful theorem that was actually recycled from the Chinese. And we needed to talk about how far we actually travel, along that diagonal. So, Pythagoras' theorem, Pythagorean theorem. Now, I love what you said, Matt, with a squared, b squared, and c squared. I'd like to write it a different way if it's okay.
That's fine.
And the reason I like to write it a different way is, if I use a, b, and c, students often put them in the wrong places. So what I like to say is, we're going to put this in terms of grade. We're going to do this in terms of grade, as opposed to in terms of in general for geometry. In terms of grade, the hypotenuse squared, so if you square the length of the hypotenuse, that's equal to the rise squared plus the run squared. And that's beautiful. It's beautifully simple. I'd rather use this than A, B, and C, because what gets lost, unfortunately, if we use A, B, and C, is where C is. C always has to be which piece? It's got to be the hypotenuse. But the lack of cohesion in hearing hypotenuse from all 40 people in this room makes me concerned. Obviously, because what people will do is they'll put the C whatever piece they don't know. And sometimes the piece you don't know is the run. Well, that's not where C is. C's always here. So I like to do it this way instead, because this way, as long as you know what pieces of the triangle are, and I think if you can figure out what these two are, you kind of know where that one is, then it's a little more, you're a little more likely to kind of get it correct as that goes. So let's figure out what is that hypotenuse in our fictitious triangle here of 100 feet and 6 feet. What is that missing piece? Well, I don't know. The hypotenuse we're calling question mark. So that's question mark squared equals, can we see that now on the camera? Am I getting too low? Almost. I'm going to put it up high. I'm going to put it up higher. Question mark squared is rise squared. So rise squared is 6 squared. I'm going to drop the units momentarily, okay? I'm going to drop the units momentarily. I don't want to focus too much on units right now. Like I said, your second project is devoted to it, but I want to talk about the units but not write them because they can get confusing. Plus the run squared, which is 100 squared. And then we end up with the hypotenuse squared. Get this out of here. Is 36 plus 10,000. With me so far? So the hypotenuse squared is 10,036. And then all we've got to do is figure out the square root of 10,036, which isn't that much more than 100. It's not that much more than 100, is it? Now, those of you using your TIs, let's throw the TI up on the board here real quick. Make sure you remember how to take a square root. This is one of those important things. Okay, let's throw the, we're still going? Yeah, we're still going. Let's throw the TI up on the screen. All right, so here's what mine looks like. Nope, you can't see that. Now you can. All right, so fire them up. Take the square root of 10,036. Square root of 10,036. Second button. Then the x squared button. You get the little square root symbol. 10,036. It doesn't let you put commas in. Whoops, I can't use the second key either. There. Strike enter. And you get 100.2 feet-ish to the nearest tenth of a foot. 100.2 feet. It's a little bit more than the 100, isn't it? And it would have to be a smidge more. It would have to be a smidge more because from horizontal, it's tilting up a little tiny bit. And in order to touch that rise that's out here, it's going to have to extend a little bit out to catch that. Now, as the angle gets steeper and steeper and steeper, it's going to have to go further and further and further to catch that rise. But when you're talking about grades like 6%, 7%, 8%, even up to 10%, that hypotenuse is going to be pretty close to the length of the run. Pretty close. Almost arguably the same value. We'll talk more about that as we go through. So, we get about 100.2 feet. Blank screen that. So that means your hypotenuse is about 100.2 feet, which again, you can see how ridiculously unscaled this picture is. Because this looks much, much longer than 2/10 of 1 foot over this one. It looks much closer over there. That red line and the run of the black line look much, much closer in length. Is that believable? This is your friend, especially when dealing with this kind of stuff. And as the angles get steeper, the hypotenuse and the runs start getting further and further away from each other. We'll come back to that and revisit that. Any questions so far? We getting grade, understanding grade? Understanding Pythagoras? You've all seen it before. The question is, does it make a little bit, either makes the same amount of sense as it did before or a little bit more. That's kind of what we're after, making sure we see both of that. Okay, I want to revisit grade up to the break. Then we can swap out memory cards and start from scratch. Okay, so I want to revisit the grade. Yeah, this is plenty of time to do that. So here's your 6% grade. What I did was, I took a little trip around Bend, since Bend is built on buttes, and took a look at some roads around Bend that you guys probably travel on a daily basis. Recognize this one? College Way. Any idea of the grade? Friends? Guesses? Huge. Give me some numbers.
22.
22%.
15.
15%.
8.
8%. 12%. It works out, on average, to be 6%. It's the same as those signs. This is the perception, right? You go up College Way, you go down College Way. My friend gave himself a concussion on College Way last year. Flying down on his new cross bike, he got very excited, new cross bike, busted his head open, wasn't wearing a helmet, going for 40. I'm so glad he didn't die. But that's the idea. He's on a bike without pedaling going 40. Imagine a car or a truck, an ATO losing its brakes. Please.
I was rear-ended going down College Way last winter.
Ooh, at the bottom by the circle,
I was at Portland.
which is basically the bottom.
Yeah.
Yeah.
And there was people passing on the
Yes.
bike lane.
Oh, God.
And the
Oh,
lady-
cars passing on the
Yeah.
bike lane. Lovely. Thank you. Don't ever do that, by the way. I will kick your ass.
And there was someone turning in front of me, and then the lady behind me was just coasting down,
Oh.
and her Toyota Corolla no longer has a dashboard. It's now the grill in her
Yeah,
dashboard.
exactly. Well, that's dashboard. It's just doing double duty.
Yeah.
Yeah. Oh boy. Yeah. It's amazing. And it doesn't take. College Way is only maybe a mile long. So you think about that grade over 5 and 6 miles, and it's surprising, 6%. Now what I did with it to get these measurements, I basically took it's a pretty consistent grade. College Way is. I just took a number of measurements with a clinometer, like we used in the avalanche class, and just kind of walked along and took. And it's pretty much a straight grade of 6%. So you're looking at that red line on College Way. But it's amazing how much speed you can pick up going 6% grade. Here's, you might recognize this one, maybe, depends on what side of town you come in from. That's Archie Briggs. That's the hairpin at Archie Briggs. Archie Briggs is definitely not a consistent grade. Depending on where you are, it levels off, and then it's got 2 steep spots. This is the steepest spot. This is the hairpin at Archie Briggs as you come down over the chutes, and then you start hairpinning around and you cut back right. There's a set of mailboxes right up here. The Tour de Central Oregon. This is the favorite Summerfest for the ride. I think you do it 6 times in a day. What do you think? Guesses for grade? Looks like it's less than 6%. And some of this is how I took the picture, too. I was trying to get you. Looks less than 6%. What do you guys think?
It's more.
More. So give me some numbers. 8. I hear 8.
8.
Second for 8.
I'm going to say 7.
Say 7? 16.7% at the hairpin. At the hairpin. Now, you guys that said 8 to 6, you're not wrong if you're talking about not just at the hairpin. I've never done the grade from bottom to top, but I've done the grade from like right around the hairpin up to where it levels off, and it's got an average grade. It's got an average grade of roughly somewhere about 10%. Because once it levels off, you're not picking up any more rise, but you're still picking up run. So 16.7 is about 17 feet per 100. If it all of a sudden levels off, and it's 17 feet per 200, the grade is now half, isn't it? It was 17%. If I then level off and go 100 more feet, it's now 9.5 or 8.5%. So you guys are not wrong when you say that. It's all a matter of what's your frame of reference. Just the hairpin, 17%. Ridiculous. But if you start looking at the entire road, it's still steep, but not as steep as that. Excellent. Excellent. One more in Bend. Might recognize this one?
Some neighborhood, I don't know.
It is. It's very close to here.
It almost looks like Portland.
It's 1 block off of College Way. It's Juniper.
Yeah, it looks like
It's Juniper. It runs the other way. Portland, I believe, is the road right on top of that hill up there. I think that's Portland. I'm pretty sure.
Okay.
It could be. That could be Saginaw. This could be Portland right here, too. I'm not exactly sure. So, essentially, what happens is this starts at the same place College Way does. But College Way starts going up while Juniper keeps going. And then Juniper kicks up and basically essentially meets College Way, maybe a little bit above it, I'm not sure. I think it's a little below it, actually. The grade on that section over there, what do you think? The grade on that section over there, the section in the back here. Ballparks, what do you think?
4.
4? Love it.
That's funny, that picture's, that
That's
doesn't show how
nine,
steep
yeah.
that is.
How steep do you think it is? Give me a grade, Kurt.
Come on, Ted, come on.
But just that section's got to, I was gonna say 20.
Yep, you're gonna say 20. 17.7% on that section. Here's why. Here's why. College Way was what, friends? 6, right? Okay.
What's with college weight? It looks like more than 6.
Well, looks are deceiving. It's deceptive. Perception is deceptive. Perception is very deceptive. When you're standing on top of Drinkwater Pass coming in off of 20, and you're looking at a 6%, you're like, holy crap, that looks steep. It's 6%. It's perception. A lot of it is because your feet are down there and your eyes are up here. A lot of that is attributed to that. When you're standing, next time you're standing on top of Black Diamond Run at Bachelor, think about how steep you think it is. And if you think of it, if you have an Android smartphone, do this for me. Install a free app called MyTracks on it.
That's such a great app.
It is. It's a free app from Google called MyTracks. Start recording at the top of the run, go to the bottom, stop recording, email me the GPS file, and we'll see how close you are to your grade. We'll do it in class. I've actually thought about that, sending some of you guys home with MyTracks running and see what your grade is as you go to your house and back. But if anybody's a bachelor and has an Android smartphone, come see me. It's a free app. We'll install it. I'm going to have you guys analyze it on your exams anyway. And we'll figure out, the perception of grade is so skewed. Perception of grade is so skewed. So here's the deal. Here's College Way in blue. Here's College Way in blue, right? What happens with Juniper is that Juniper essentially goes flat and then rockets up to get to the same height. So when I say it's a 17.7% grade, I'm only talking about that part right there. Assuming those two profiles are indeed College Way and Juniper, what's the average grade on Juniper from Greenwood to Portland? It's almost a trick question. Remember, College Way was 6%. So assuming that blue line up there, that blue line, this is a 6% grade. This is almost a trick question. What's the average grade for Juniper over the same run? 6%. 6%. Isn't it? Because you start at the same spot as College Way, and you get to the same spot as College Way. So you have the same rise and the same run, but you got there in 2 different ways. Huh? This happens all the time. We talk about average speed. I go for bike rides with my friends back east for road bike rides. And we'd always get to the end of rides, and I'd always have the same average speed as them. I beat them up every single hill. Every single hill I beat them up. But I always had the same average speed, and I realized why. When I got to the top of the hill waiting for them, I didn't just stop. I'd ride around in circles. So in other words, I was moving the same amount of time, essentially, they were, with a minimal number of distance, but the difference in time averaged the speeds out, distance over time. The distance was minimal, so I wasn't going anywhere. But I was traveling the whole entire time. Once I figured that out, I needed to the top of the hill and sit there. Then my average speed went way the hell up, because my time went down. Same thing here. If you get from here to here, you cover the same rise over the same run. There's no difference. There's no difference in grade. The 17.7 is just this part right here. Because you have all that rise over roughly 1/3 of the run, which makes it 3 times steeper. Does that kind of make sense, friends? Good stuff. Let's leave Bend. What's the first thing that comes to mind?
Europe.
Used to be Europe. Now it's blood, doping, and criminals. But it's the Tour de France. I used to follow professional cycling. It makes me sick to think about it now. Anyway, that's I believe the Galabert Pass, I think. Yep, that's the Galabert Pass. Average rate is 7.1%. So you think to yourself, oh my God, why are these guys working so hard? It's 7%. It's the same as College Way. They do it for like 20 miles. And they're doing it at like 22 miles an hour. It's ridiculous. Of course, they're also doped to the gills, so I don't know how much credit you want to give them. That's the Galabert Pass. I love this shot.
Yeah.
This is Mont Ventoux. Is that this one? No, Alpe d'Huez. This is the Alps, not the Pyrenees. This is Alpe d'Huez. This is one of the hardest climbs in the Tour, with an average grade of 8%. But what's cool is you can actually see it in this picture. This is a steep hairpin, so that's an average grade of 8%. That hairpin is steeper than 8%, but it averages out. At the end of the day, you've risen 1/8 as much as you've run, if you will, which is the 8%, or 1/12, I should say, 1/12 as much. Cool so far? All right, back to America. Name the town. Hell yeah, San Francisco. Hell yeah, San Francisco. And I love this shot because you can actually see the 19% grade. Look at the triangles. Right there. Isn't that badass? So there's 20, there's 100-ish. I mean, you can actually just do this. Like there's 1, 2, 3, well, not quite. 1, 2, 3, 4, 5. There's your 20%, roughly 1/5. So for every foot of rise, you have to pick up 5 feet of run. But that's not even close to the steepest street San Fran has to offer. That's not even close. Name it.
Lombard.
Name it. Yep. There's Lombard, 28.7% grade average. 28%. I think you can still drive on it, I'm pretty sure. Pretty sure. But that's not even the steepest one San Fran has. Filbert. Filbert is the steepest one in San Fran. Give me the grade, friends.
32.
Damn close. Damn close. You can't see it in this picture. I'll have this PowerPoint for you guys later. You can't see it in the picture. The sidewalk has the little 2x4s bolted into it. So when you're walking up, you have something to push against. Because it feels like you're going to slide backwards. It's that steep. You can see it. You can see it on the monitor a little bit better.
Oh, yeah.
Yeah. It's so steep. Please tell me your name.
Dave,
Gabe, go.
if you have time at home, get on YouTube and watch SF MASH.
Yes.
It's a bunch of Fixie kids, and they live in San Francisco.
Those guys are
It's called
insane.
These hills, and it's like the
Fixies on these hills. You got to have young knees.
Yeah, you gotta have a lot of things.
Surprised they can play, if you know what I mean. Well, speaking of that, Gabe, let's leave America and go to New Zealand. I heard a great story about a biker. This is Baldwin Street in Dunedin. I heard a story about not a fixie biker, but a biker on a multi-speed bike tried to ride up this. He got, the road actually does this. It does like Juniper. It starts like this and then rockets up. He started riding up this part. His rear hub exploded from the torque, which goes to show you how strong his legs were. That's pretty amazing. His legs didn't give out what the hub did. This is Baldwin in Dunedin, 35%. Which, if you think about it, is only a couple percent more than Filbert was. But because this shot is taken the way it's taken, you can actually see that slope of 1 to 3. That's essentially a 1 to 3 slope, essentially. Which means if you drop in the rise, it's essentially 1/3 of the run. So you got 1, 2, 3. Essentially, it's a 1 to 3. Go ahead, go, please.
There's a road that goes down onto the beach in, I want to say Lincoln City or Newport. and it's
Excellent.
38 degrees.
It's 8 degrees.
It's 38%.
It's 38 degrees or percent? 38%. Believe it or not. That is ludicrous.
My bumper got stuck in the sand.
I believe it. I believe it. That happens. Believe it or not, though, there's a road in America that beats it. Guess what state?
Why? West Virginia.
Close.
New Jersey.
Closer. Pennsylvania. Guess what town?
Pittsburgh.
There it is. It's Pittsburgh. It's Pittsburgh. Canton Avenue. Oh, it doesn't beat it. I thought it beat it. 38 does beat it by 1%. I thought Canton was over the 40s. You can see a picture of it. They put this on a cyclocross race. 37%. What do you guys have to do? Forget my bike and my shoes. I'm going to run. You can see, look at the steps. Look at this poor guy. He's actually doing it. But look at this. Look at the steps next to it over there. Look at the steps. Look at the steep those steps. 37% grade. Ludicrous. But guess what they did in Florida? They built driveways. Talk about getting your bumper stuck. Echo. Unbelievable. Did you remember the bumper?
Yeah, I went to go up and
Yes. I approximated it at 40%. I have no idea what it actually is. Obviously, they don't get snow there. So. All right, so let's pause this, save some space. We were. All right. So let's segue into where we're. There's something burning over there. That look legit?
They said they were going to start. They said they were going to start burning.
Sorry, ADD. Can't say.
I'm a little curious about how the fire's going.
So here's some data that we're going to play with. And I know it's a bit dated, and that's okay. That's part of the point. Is I want to bring this into the current day here. What I collected here from USA Today, from 92 to 2000, rough amounts of Americans under age 65 uninsured, no health insurance. So in 92, you had 35 million folks. 94, you had 38 million, and so forth and so on. And then another way of looking at it, same data over there, is just with smaller numbers. Like, in other words, take some of the zeros off and take some of the thousands off and bring it down to size. So 2 means 1992, 4 means 1994, and so forth and so on. if I was to ask you to predict how many uninsured people there were in the United States right now, what would you say based off of this? Let's make a big assumption here, too. Let's make a big assumption. Let's assume that the rate of uninsured has changed in the same way from 92 to 2000 as it has from 2000 to 2013, where we currently are. Let's make that assumption. We'll revisit that assumption later, because part of statistics, which is kind of what this is living in, this vein is living in, is being able to decide if your assumption is valid. Go ahead, Quincy. Yeah.
I was gonna say we just make an equation.
Well, how? I love that, my friend.
Well, you should start.
I should start. No, I like the way you started. Did you hear Quincy's idea? She said we should make an equation. I think it's freaking awesome. What do you think, Kelly?
Well, you figure if it's 8 years.
Uh-huh.
You figure the difference between those 8 years, how many happened between 30?
Oh, I see what you're saying. So Kelly's saying, so from 2 to 10, there's 8 years. 35 to 44, that's at 9 million people. So a good indicator would be, let's go 9 million people every 8 years. So in 2008, we would have picked up 9 million more, which would have been 53 million, right? Did that right? Yeah. And then 2012 would have been 4.5 more. So then we're up to 53 plus 57.5 million. I like that. Why would you use the first and last data points? Just out of curiosity.
Just to give yourself an average.
I love that idea of an average. The only thing I'm concerned about, and this is a concern I have, is I'm thinking about that picture over there. Right, I'm thinking about that picture over there, and I'm thinking, okay, if I use just first and just end, yes, it is an average. That's 100% correct you use of that word. But is that average the best way to look at it? And I don't know the answer to that entirely, because it ignores these guys in the middle, and there's only 5 data points here, for sure. But if there were many more, should we be looking at those other ones as well? I'm not sure of the answer to that question. Let's keep that idea on the back burner, Kelly, if you don't mind. If you don't mind, I want to keep that idea on the back and revisit it. Why would we even think about trying to make the argument I just did when we said, okay, that's about 9 million people every 8 years. Let's write that down. So, method number 1, we see a rise of about 9 million people over a run of 8 years. So, and that's the logic we kind of worked with, didn't we? We said, yeah, it's 9 for every 8. What are you immediately assigning to that data set when you do that? You're immediately insinuating that the data is following what kind of a pattern?
Linear.
Consistently linear. I love that. Consistent, linear, they mean almost the same thing. No, they mean the same thing, right? It's consistent. Oh, sorry. Consistent, linear. Basically, you're assuming that the rise and the run are staying consistent from data point to data point. And this was my concern with using just the first and the last. Kel, was that is that a fair, consistent measure? Well, let's take a look at the data again, okay? Let's take a look at the data again. Okay.
Count the variables.
Let's take a quick, exactly, that's what I'm saying too. So let's use this because it's easier to deal with. So over 8 years, it went up 9 million. Let's see if we can work backward, we can reverse engineer from that. How about the first 2 years? 3. So 3 million every 2 years. Let's make this a little bit more organized. Between, so we already did 92 and 2000. And I'm going to put this slope in quotes over here. Our slope was 9 over 8. And the units of our slope are millions per year. Millions per year, right? Millions uninsured per year. Now 9 over 8, let's make this easier to think about. That's 1 and an eighth, and eighth is 12 and a half. So that's 1.125 per 1. So pretty much every year, you're picking up about 1 and 1/8 million people more that are becoming uninsured. We can also look between just 1992, and 1994. Now that's only 2 years, and the uninsured went up 3 million over 2. Well, that's 1.5 per 1. So that's a little bit more than it was over the entire realm of 92 to 2000. So we're getting an idea of what's actually happening. If you look at this, this is a little bit of an exaggeration over here. But if you think of this as a two-dimensional graph, kind of, it's like looking at the difference between here and here and here and here. 1.5 is steeper than 1.125. So that slope between those 2 points is steeper. Let's look at some other pairs off. What other years should we use, do you think? Draw out some. Give me some years. 1996 to 98. Go for it. 98. Again, 2 years. 2 years different. 2 years different. 39 to 41. That's 2 million for 2 years. That's exactly 1. So over the course of those 2 years, we average 1 million more per year. This is all per year. So 1.8 million per year, 1.5 million per year, 1 per year. Does it ever drop below 1 per year? Does the slope ever drop below 1 million per year? Careful, careful. These years jump by 2. Yeah, 94 to 96, it increases by 1 million over 2 years. So that's half a million a year. So the rate of uninsured slowed from 94 to 96 on average. On average. On average. It could have been higher in 1 year or lower in another year, but on average it's. So the question I have is, if we're getting these different numbers, 1.125, 1.5, 1, a half, which one do we actually use as the slope, right? Which one do we actually use as the slope? Now, what I do feel pretty good about is the fact that we're getting relatively consistent numbers, 1.125, 1.5, 1. They're pretty much in the neighborhood. I do want to talk about a very efficient way of looking at this data. So this data is great, except I keep looking over at that board and I want to use that picture, but that picture is not accurate to this data. But there is a way of lining up this data in a way that does make it two-dimensional and therefore easier to see. Exactly, my friend. It's called a scatter plot. And it's called a scatter plot. This right here is a scatter plot of those exact same data. Please pardon the robot arm in the middle. There's a 4 right there and a 6 right here. So you've got 0, 2, 4, 6, 8, and 10, 12 years since 1990. So 1992, 1994, 1996, so forth and so on. Up there, you've got millions of people that are uninsured with no health insurance. And this way, each point tells you something about the situation for that year. So this point right here, what are the coordinates of this point right here? 2, comma, which means what? In context. That's the coordinates, perfect coordinates.
Y and X.
Y at X. Good. Give me some context though too. I love that, Tiffany. But give me some context. To what for 35 what? 2 years after 1990 or 1992.
3 years and people.
Yep. How many people?
35
35 million people were uninsured. Exactly. So in 2 comma 35, damn it, Sean, that's what it says. You're right, it does. It does, but it's got context though. In 1992, 35 million folks were uninsured under the age of 65 in the U.S. 1994, 38 million people were uninsured. 1996, 39 million people. Now what's cool about looking at it this way is you can see all of our slopes, right? Kelly, your slope of 1.125 would be found by connecting this point out to that point. But you see the small problem with doing that, if we actually, can I draw on this? Let's try with this little highlighter. Nope. If this was Word, I could do it. Let me slick. Yes, I can, yes, I can. Hang on, I'm gonna be slick. Flipping tool. Okay, there we go. Make it thicker too. There we go. Pretend that's a line. Let's undo that. Damn it, I need a ruler. This thing doesn't have a ruler, I don't think. Pretend that's a line. I was looking, I brought this stuff on overheads and I was going to actually draw on the thing with a damn straight edge, but pretend that's a line. So even, it's ish a line. The problem with it is, we miss these points in the middle These are called residuals. You don't have to know what that means or even what that's called. It's called a residual. And the more off you are, the more error you have in your actual estimate of that line. So there, but that one has the slope of 1.125 million per year. Our second one was 1.5 from 92 to 94. Let's change the color of the pen to red. That was this one right here. And I'm thinking that's not a good one. That was my idea. I think my idea sucks. Because you see what happens if we use those first 2 points? The model is too steep, and it gets too far away from the other points. See what I'm getting at there? It's too far from the other points. So I'm thinking my idea sucks. I think we let that one go. How about 96 to 98? How many more colors do we have? We've got black pen. 96 to 98. What do you guys think about this as model? What do you think about that one? Pretend that's not there. I hit the side of the damn tray. What do you think about that black line right there? Who do we like the best of the three that are up there, I guess?
The black.
Oh, we like the black one the best. Okay. Now, we verbally said, we also used 94 to 96, didn't we? We said, I asked, is there anywhere where the average slope is less than $1 million per year? And you guys, I think 94 to 96. Should we use that one? Let's see if this highlighter works. Should we use that one? I think that's kind of crappy. That's too low. So we kind of like the black line, which would have a slope of 1, right? And the thing is, we can try this all day long, can't we? I mean, we could try 98 to 2000. Try that one. We could try 92 to 96, which is not all that bad. And we can recalculate these all day long. But the problem is, every time we try one of those, wait, spaghetti up there. Every time we try one of those lines, we're starting from 2 of the data points that are already on the curve, right? That are already on the data set. The somewhat confusing part about this is you don't have to. All of those lines I just drew have some element of error involved in them. There's one line, and you guys may have played with this in Math 95. There is one line called the best fit regression line that fits the data points the best, which means the residual error is minimized. And I got news for you, it's none of these. It's not one of these. The best fit line for this data doesn't touch any of the data points. Here, it's actually right here. It's actually right here. That's the best fit data point. That's the best fit line for those data points. The slope, the best fit slope to 2 decimals is 1.05, which is dead close to everything we had today. 1.5, 1.125, 1. It's in the neighborhood. But that's the best fitting slope, which means on average, the best estimate for how many uninsured we pick up each year is 1.05 million per year. And the 333.1 that's out there at the tail end, the y-intercept, we'll come back to that too later. How do we feel about that red line, especially compared to the other ones we were scratching up a few moments ago?
Very confident.
We okay with that? Are we still living with the votes of Kelly, you said consistent, right? And Lynn, I believe you said linear. Are we still okay with even approximating this? Because what we're about to start doing is this idea of linear modeling. We're going to be linearly modeling a data set. Now, when you see modeling, I remember I used this word for years and years and years, and finally a brave student asked me a few weeks into the course, so this is modeling. Is this like Tyra Banks modeling? And I didn't realize, like, oh my God, I'm using this word. I'm using this word that has a completely different meaning outside of the context of math class. So all we're talking about with linear modeling is, how can we look at that data, identify it as linear? This is why the scatter plot is so important. Look at the data. Because the very first thing we did was we said, oh, okay, from 92 to 2000, we went up 9 million over 8 years. So that's 9/8. Big assumption right there was that it was linear. That's where the scatter plot comes in. Look at the scatter plot and say, okay, yeah, it kind of does look like a line. It's rising in a fairly predictable pattern. Just like I told you guys with the syllabus on Tuesday. There's a nice correlation, a linear correlation. The more quizzes you turn in, on average, the higher students' grades are. I can't say it proves it. I can't say it proves why the grades are higher, but there's a nice correlation that looks just like this. So when I talk about linear modeling, all that means is we're finding a linear equation, that best describes a linear-looking data set. I'm going to put that in quotes. I'm going to put that in quotes because sometimes data sets don't look linear. But when they do appear to be linear, and we have technology to help us kind of assess that, when they do look linear, then we have a model. And that's what linear modeling is all about. That's what modeling in general is about, is finding some kind of a mathematical equation or a formula or a function or a construct that describes what's actually happening. What we do with those models, we have to be careful with, and we'll talk more about that as we go through the course too. But right now, the question is, where did that line come from? I told you the kind of surprising fact that that line doesn't actually pass through any of the data points. Do you see the residuals, friends? Can you see the residuals up there? Yeah. Got one right there. So you got these residuals, and the sum of those residuals is minimized with the best fit line. So in other words, we're off the least. That's why it's called the best fit line and not a thank you. I heard over here too. Not a perfect fit line. It's the best fit line. It fits it the best it can. What would the data points have to look like if it was a perfect fit line? Exactly. Wait. Cheryl. Yes, there we go. Right, Cheryl. They have to be on the line. Over 2, up 1. Over 2, up 1. Over 2, or something along those lines. No pun intended. So you've got this. So the question now is, how do you come up with that 1.05 million more uninsured per year, and 33.1? Well, quick and easy answer. Here's the formulas for it. I mean, it's a quick and easy answer. It's not a quick and easy computation. So, better than that, you mute the screen. And what I've got here is I've got a little booklet I've printed off for you guys. Keep this around with you. This teaches you how to put data points into your TI, create a scatter plot, and find a best fit line on the data points. It'll also, later on, over the next 3 and 4 weeks, teach us how to do quadratic regressions when we drag my bike out there and you time me going down the hill. And it'll also have us, exactly, that's very common. Hopefully it's raining very hard that day. Awesome.